Alright everyone, welcome to today's video. We're going to continue talking about NMR spectroscopy, and this time we'll talk specifically about spectrum and how we interpret the spectrum and things of that nature, right? So, right, last time, or the last video, right, we finished up talking about chemical shifts and what is a chemical shift and how we expect chemical shifts to vary with molecules, okay? And so a lot of time, so here what's given in this figure in this slide, right, is just kind of showing you roughly where certain chemical shifts values are. Okay, so 0, to say 300, right, kind of chemical shift range, right? So when you have just carbon attached to some other carbons and kind of an alkane type thing, right, very low chemical shifts, right? You have like carbon bonded with oxygens, double bonded kind of carbons, or aromatic carbon, and things like that, right? The shifts can get larger and larger and larger. Or if you have a radical, okay, because then that radical electron strongly interacts with the electric field and can cause a very large shift, right? And so there's these wide ranges of where chemical shifts kind of typically appear, right? And so we know a lot of this stuff beforehand, right? We have ideas of, this type of a local environment will have this type of a chemical shift for my molecule, okay? And that's kind of what we use then to understand things and be able to predict structures of molecules given NMR spectrum. Okay. So we look at a couple of things. We look at chemical shifts, but we also look at the fact, as we'll see, right, that there can be many peaks that appear in a spectrum, okay? And not just because there's different chemical shifts, but the peak itself can kind of be split in an NMR spectrum, right? And how this works, right, is if I have two particles, okay, each, say, nucleus, right, say these are two nuclei, so each nucleus has a spin quantum number of 1, right? So again, I could call this, instead of L, I could say this is I equals 1, right? So I have two nuclei, each with a spin angular momentum of 1, right? Then the total, right, angular momentum is going to either be 2, 1, or 0, right? Okay. And here I'm kind of giving the idea of, right, if you had two tops spinning, right, and they're both spinning in the same direction, and the total angular momentum in that system adds together, while if they're spinning opposite direction, the angular momentum, right, the destructively add, right, is kind of the example here, right? But again, the idea is, right, you're adding this angular momentum together in the direction of the spin of these two nuclei, right, whether they're pointing the same direction, perpendicular to each other, or pointing in the opposite direction, right, affects what the total spin is in your system, okay? Right? And so that total spin then can vary, and then those total spins can have different, directions themselves, right? If my I were equal to, right, then my m sub I would be values of -2, -1, 0, 1, and 2, right? And then each of those would interact differently with the external magnetic field, right? And give different energy levels and things like that, right? And so here, looking at just a spin 1/2 system, okay? And let's say I have two different atoms, okay? You could do this with the same atoms, but we'll do it with two different atoms, atom A and atom X, right? So the total spin when these two nuclei interacting with each other, right, can be that both atoms have up spin, one has up and one has down, or both atoms have down spin, okay? Right, if I were to just imagine that sorry, right, if I were to imagine that these spins aren't interacting with each other, right, I just literally have two spins that each have their own energy, right, there's no interaction, right, I would just add the energy for the two spins together. Sorry, I got thrown off because I was looking at this equation. There should be a plus sign, right? I should be adding these two energies together. There's no reason why I should be taking the difference, okay? So I'm adding the two energies together from the two different nuclei, right? And then this will give us four different energy levels, right? Where there will be an energy level, right, corresponding to like alpha X, alpha A, right? Some energy level alpha X, beta A, some energy level beta X alpha A, some energy that's beta X beta A, right? Assuming a magnetic field, right, in an external magnetic field, right? Right. If this is not in any magnetic field, these all have the same energy. Okay. Now I drew four distinct levels because I'm assuming A and X are different. If A and X are the same, then this reduces down to just three distinct energy levels. Okay. And so it depends if A and X are the same or not. Okay, but assuming they're not, then they have four unique energy levels in an external magnetic field. Okay, this is assuming there's no coupling, no interaction between these spins, which we're going to add that in just a minute. Okay, right, and so again, so I'm going to start off here on the left side with no spins interacting. Okay, so I have these four energy levels I talked about, okay? And then what I'm going to assume is that these spins are interacting, right? And their interaction is given by this coupling J, okay? So J represents kind of the strength of the interaction between these spins, okay? So it could be something like the energy contribution here, something like J times M sub L, or not M sub L, we should do M sub I of A and M sub I of X, right? Right, and then probably like an H here or something like that, right? Some H bar times J, right? So this would sort of be the energy term for the coupling, right? It is related with the spin on state I times spin on atom A, spin on atom X, okay? And then just some coupling J, some strength of coupling between those guys, right? And so when these things couple, what will happen is your four energy levels will change, right? Based off of this coupling. Now here, I still have four energy levels, but now, right, the splitting's a little different, okay? Right? The splitting, okay, before, right, when I just had my uncoupled peaks, right, I had alpha, let's call this for X and A, right, beta, alpha, beta, 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 okay? And when we probe something in NMR spectroscopy, okay, when we're doing NMR spectroscopy, right, we're going to flip a spin at a time in that probe, right? So when the light interacts with the system and induces a change, it's changing one spin at a time. So I'm not going from alpha, alpha to beta, beta, okay? I'm only able to go, say, from alpha, alpha to beta, alpha, or alpha, alpha to alpha, beta, okay? So I have, you know, these energy gaps. Let's change the color. I should change the color to kind of highlight the different energy gaps we have here, right? So different possible energy gaps are, say, there to there, there to there, right? Otherwise, I can go beta alpha to beta beta, or alpha beta to beta beta, right? And what if I drew this appropriately, what you'll find is that you'll have just two energy gaps, okay, corresponding to like alpha X going to beta X, and one energy gap corresponding to alpha A going to beta A, Okay, so there will just be two energy gaps. If your spins aren't coupling with each other, that's all you're going to get. It's two energy gaps, of course, and so right, and the the location of this energy gap, right, the value of the energy gap, right, depends on the effective external magnetic field reaching your nucleus, which depends on the chemical shift, right, and so this will depend on sigma x, right, and this will depend on sigma a, right. So these two peaks will be located different in a plot where I'm plotting sort of the chemical shift, right. If I'm plotting, say, the chemical shift on my x-axis here, right, I'll get a peak corresponding to x, and a peak corresponding to a. Okay, I'm going to switch around the location here, right. So again, this is without any coupling between our nuclei. I will get one peak corresponding to wherever atom A is, and one peak corresponding to wherever atom X is. Okay, and that's in terms of their chemical shift, right? That these two atoms are different; they have different chemical shifts. Okay, and there's only going to be two energy gaps I can probe, and it's because, right, I can flip one spin at a time, right? Well, if I now allow these things to couple together, right, I allow atom X and atom A to couple together, and I introduce that coupling, right, that we talked about in the previous slide, that depends on J. Okay, J is the strength of the coupling, right? Again, I said that like E coupling is roughly equal to, say, H times J times I, not I, sorry, it should be M sub I, right? M sub I of A, M sub I of X, right? And so that's roughly what the coupling is related to. Okay. And so if I introduce this coupling, the energy levels then split a little more. Okay. So here, what I've plotted are the energy levels. In the left figure here, you have then energy levels with the coupling. Okay, so this is with coupling. Okay, and what happens again? We can only change one spin at a time. So here, for example, this line, right? I'm changing right atom A from an alpha to beta spin. Similarly, this line here, right? I'm changing atom A from an alpha to beta spin, okay? While this line here, I'm changing alpha X, or atom X from alpha to beta spin, okay? And this line here, right, I'm changing, again, atom X from an alpha to beta spin, right? So I have these still changes in spins, right? I tried to use some different colors here, and maybe I'll try to color code this one a little bit, right? But I'm using different colors for each of these different transitions, okay, to indicate or try to emphasize the fact that even if it's not completely obvious to see, it's a little bit more obvious for the blue and green, but if it's not obvious to see, right, the energy gaps are no longer the same, okay? These energy gaps are not the same. The blue and green are not equal in length. The red and yellow are not equal in length, okay? And the difference in the length of those splittings is directly related with coupling J, okay? And so what happens in a spectrum for NMR, right, is again, here, my top hand-drawn spectrum here, right, has no coupling, right? So no coupling, two atoms, I just get two different chemical shifts, two different peaks in my spectrum based off of those two unique chemical shifts, okay? Right, but if the nuclei couple together, then both of those peaks get split into two peaks themselves, okay? Where again, here, right, so this delta A, this is like my sigma A, right? Okay, my shift for atom A, right, is getting shift, right? So I would, without any coupling, I would have a peak that goes right in between these two, right? But because there's a coupling, now that is split into two peaks, right? Shifted 1/2 J and, up and down, okay? and the same thing happens with atom X, right? So again, so what we can measure and all the unique information we can get from NMR spectra, okay, and this is just for looking at chemical shifts. There's a lot of different types of NMR spectroscopy looking at a variety of things that can give us even more information about atoms and molecules based off of the nuclear spins of the atoms in your molecules, right? But here, just focusing on studying chemical shifts, okay, and the fact that if I measure the energy gaps induced by an external magnetic field on my nucleus, okay, I can get unique information based off of the local environment related to the chemical shifts, as well as how strongly different nuclei are coupling together, right, to induce a splitting in the peak, okay? And this nuclear coupling, right, is going to have a distance dependence, right? So for two nuclei to couple together, there will need to be a close contact between those two nuclei, okay? So the two nuclei have to be locally close together in space for there to be this coupling, okay? So we can get some information about your molecule, and so you get a lot of structural information as well as electronic information potentially from your molecule by studying these chemical shifts in these NMR spectrum. Okay, and so trying to expand upon this, right, is if I have, say, two X atoms now coupling with my atom A, okay, what happens to the chemical shift in atom A is it will get split into three peaks now, okay? If I have three atoms coupling with atom A, it gets shifted into four peaks, okay? And the heights of these peaks are 2 to 1 to 1. The heights of these peaks are 1 to 3 to 3 to 1, okay? So the ratio between the heights in these peaks are very specific, okay? And they are kind of dependent on how many identical atoms are coupling to your nucleus A that say you're studying, right? So here I'm just focusing on the chemical shift for atom A, and I say I have two identical atoms, X's, that couple together, and that will split it into three peaks. And I say I have three atom X's that splits into four, and they have very unique peak height ratios, okay? And so this, these little figures here are trying to help show and represent how you get those peak heights and where this is coming from. This is kind of like, let's see, it's, so this is kind of obtained through something called Pascal's triangle, right? So what you have is you have, say, atom A by itself, not coupled with anything, right? Just has its one peak. If it couples with one thing, that peak gets split into two, okay? That then, if you introduce a new atom X, right? So this is just one X. Now if I have X2, right? Well, that X is now splitting these peaks equally, okay? And so now I get two peaks here, right? These are two different peaks, right? And those two peaks each have the same kind of energy that they appear in your spectrum. So the amplitude is doubled there, right? And so that's why I have 1 to 2 to 1 for AX2, right? And then these peaks split, right? And then each one of these two split, right? I didn't give myself a lot of room here, right? But each one of these two peaks split, right? Oh, I drew that wrong. Sorry, I introduced way too many peaks here. Right, so this splits out, this splits in, and then there's another one that splits there, that splits there, splits there, there, there. That's right. So you have these two peaks contributing two to those. So you have 3, 3, 1, 1, and then again that splits into there, splits there 3 times. There'll be a split in the middle that has 1, 2, 3, and then another 1, 2, 3. Like I got too many lines here to really be able to see everything, right? But 1, 2, 3, 4, and 1, and so you'll have a ratio of 1 to 4 to 6 to 4 to 1 for your peak heights. Okay, for x cubed, right? Or sorry, not x cubed, x4x, four different x's coupling with a, right? And it goes on and on and on, right? And this is referred to as Pascal's triangle, right? And that can give you information as to which, how many, right? So the number of peaks, right, that get your chemical shift gets split into, right? And then the ratio of peak heights in those peaks tells you how many identical atoms are coupling to that nucleus, okay? And then that can give you structural information, right? That can tell you a lot about where certain atoms are bonded and certain functional groups are bonded and things like that. Okay, because again, the coupling J between the different nuclei depend on the type of nuclei, right? How far away they are, and other things like that. Okay, and so there's a lot of information you can get through the splittings of your chemical shifts in NMR spectrum. Okay, and so that will kind of be it for this video on NMR spectra. Okay, we talked again about chemical shifts and how that appears in your spectra, and then when nuclei couple together, how that impacts where those peaks are for those shifts, right? And the type of information we can potentially learn from studying chemical shifts in NMR spectrum.